Hi, this is Mrs. Yenny, and I'm going to go through 2.2 review of the problem. And this is the maze problem, choosing paths. The whole gist of this problem is that this is actually a game. It's a maze game, and probability comes into play here because you have to make random choices at each of the forks in the path to determine which cave you end up in. One of the interesting things about this problem is typically kids look at this and they say, it's just a 50-50 chance, what's the big deal? Because they see that there are 1, 2, 3 paths that end up entering into cave B, and then they see that there are 1, 2, 3 paths that end up entering into cave A. And so they automatically assume that that means that it's a 50-50 chance, fair game, and why would we be analyzing the probability? Well, it's not the case. This is actually an example of a dependent event, and it's a new kind of probability outcome for us. We're looking at an original path and what happens to it at various points along the path. So what we're going to do is we're going to simulate this game being played 18 times. To do that, we're going to basically travel along this path, and when we get to this fork in the path right here, you'll notice that the path splits into 3 parts. So I have to think of some way I can simulate a random choice of the path splitting into thirds. Well, what I've chosen to use is this spinner. This spinner I have labeled upper path, lower path, and middle path. And what I'll do when I get to this point in the path is I'll simply use my spinner and I will spin. And for example, in that example, I ended up in the middle path. So in that example, I would go from here down the middle, and then I would write down, because I'm keeping track of these 18 attempts, I would write down cave A. So I'm going to go ahead and just do another example. So upper path is the next example. So here, trial number 2, I have now chosen randomly upper path. But you'll notice that the upper path splits again right here. So now I have to figure out a way where I can simulate a choice of 2 separate paths here, a random choice. What I'm going to do is I'm going to use a die. So I like to spin the die, or roll the die here, and if it's an odd number, we're going to go at the upper path, and if it's an even number, we'll go to the bottom path. And in this case, it was an even number. And so you see that we end up in cave A, so I'll write down cave A again. If by chance when I made my first original spin for this point in the path, I ended up here at lower path, I would have another decision to make right here, and this decision is again a decision of thirds. So in this case I would spin the spinner again and call this the upper and middle and the lower path. So I did this and I played 18 times, and now I'll show you my results because I kept track of my results and I have them right here. You can see that after 18 times I ended up in cave A 10 of those 18, and in cave B 8 of those 18. So I'm going to write my experimental probabilities. Remember, we always write our probabilities as fraction decimal percent equivalents. So this becomes 5 ninths, which is, I'm going to round it to 56%. And this, of course, becomes 4 ninths, which is 0.4 repeating. And I'm going to say about 44%. Okay, so they look pretty close to 50-50, but I'm not convinced quite yet. So we're going to go to the next part, part C. And what we have in part C is we have a start of an area model. And so the example is that a student in this class that we're learning about has taken an area model and split it into thirds. And we have to explain what's going on here. Well, to explain it, I'm going to talk about the whole square. So the entire square represents the original path. And remember back to that maze, what happened to the original path? Remember, the original path is what we're following here, and then the original path at this point split into thirds. And so by representing the whole path, the whole original path, as this square, that's why we split it into thirds, to get our upper, middle, and lower path. So now what I'm going to do is I'm going to complete the area model so that we can use it to help us find the theoretical probability. So the upper path, if you remember right, splits into 2 parts. And one of those parts goes to cave B, and the other path ends up in cave A. The middle path, remember, goes directly into cave A. And the bottom path splits actually into thirds. And one of those thirds ends up in cave A, and two of those thirds end up in cave B. So to find our theoretical probability, what we're going to have to do is add up our fractional pieces, because remember back to the Investigation 2 lecture, we talked about an area model utilizing the fractional parts of an area to be able to calculate the probabilities. So this A, I have to figure out how much of the whole it takes up. Well, you might be thinking half, but it's not half of the whole. It's half of this section. It is 1, 2, 3, 4, 5, 6, or 1/6 of the whole. So I'm going to add 1/6. Plus I'm going to add how much of the whole this section takes up, which is 1/3 of the whole. And then I'm going to add up this little piece. How much of the whole does this little piece take up? And that's 1/9. And anytime we add fractions, as you know, we have to turn them into their denominators into like denominators. So I'm going to use 18 as my denominator. 1/6 is the same as 3/18. 1/3 is the same as 6/18. And 1/9 is the same as 2/18. Now I can add it all up and I get 6 plus 3 plus 2, which is 11/18. So cave A, the probability of ending up in cave A is 11/18, which is the same as about 61%. I'm going to circle that for cave A. Now I could do the same thing for cave B. I could add up this 1/6 and these 2/9, and I would end up with what's left from 11/18, which of course would be 7/18. But what I'm going to do also is I'm going to double check myself by taking 100 minus 61, and that's just simply going to give me the probability of cave B, because I remember that the whole thing is 100%. So I'm left with 39% for cave B. So you can see that it's obviously not a 50-50 chance. Alright, so to compare my theoretical and experimental probabilities, they were fairly close, but 56 to 61, 44 to 39, fairly close. The reason that my experimental and my theoretical probabilities aren't closer, they don't match, is because look how many trials I did. Only 18 trials. That's not very many. So I can't expect them to be actually matching at this point in time. Alright, let's go to the last part, which is comparing our creating a path from this path. So this is an area model, and we're going to work backwards now. So to create a maze, I can see that I have a cave A and a cave B. So I'm going to make my little caves. I'm calling the inside one A and the outside one B. And now I'm going to have an original path, and my original path splits into thirds. So I'm going to split it into thirds. My upper path, I can see, splits in half. 1/2 going to B and 1/2, oops, 1/2 going to B and 1/2 going to A, and there's my split. The second path goes directly to A, so here's my second path, go right to A. And then my bottom path actually splits in half here, and two of those halves, well, it splits in half and then it splits in half again, which is kind of strange. So two of those, so there's a split here and there's a split here. So I'm going to show a split here, and then I'm going to show a split here. So it splits in half, and then it splits in half here, and it splits in half here. Two of those, both of those go to A and both of those go to B. Alright, so now I want to find the theoretical probability of ending up in room A and in room B. Well, last time I calculated the theoretical probability of A, and then I just subtracted from 100 to get B. So let's do that here, but this time let's calculate it for B instead. So this part of B is, again, 1/2 of a third, which is 1/6. And again, I'm finding room B. Then down here, each of these B parts are 1/4 of a third, and 1/4 of a third, of course, is 1/12. And if you need to actually look at that, you can sort of imagine how many of these would it take to cover the whole thing. 4 here, 4 here, and 4 here. So together, that would be 2/12. So I'm just going to rewrite this whole thing. 1/6 is also known as 2/12, plus I'm adding 2 more 12ths, and 2/12 plus 2/12, of course, is 4/12, which is the same as 1/3, which we all know to be 33 and 1/3%. So if that's B, then I know A is going to, I'm going to work backwards here. A is going to be 66 2/3%, also known, of course, as 2/3. So those are my final answers. All right, thanks for listening, everybody. I hope that was helpful. If you still have questions on 2.2, make sure that you come see me and clarify, because there's some big stuff in this problem. All right, good luck.